everyone. In this video, I continue the lecture series on STKO that I have started. And up to this point, I have covered the home tab, the geometry, the introduction. Um I also have done some discussion on the preprocessor module overall and post-processor. However, this is now a detailed discussion on the STKO, and I have covered all these options as well as I have covered all these options, and some of these options are also covered in the discussion as well as this one. Now I am discussing the local access, sorry, the properties module. And in the properties module, there are a lot of options available. Uh, and if we look at here, we have these techniques that is it is divided into five main sections: the local access, the definitions, physical properties, element properties, and visualization module. So somehow I will try to discuss them one by one, but at some points we have a very detailed discussions on a lot of models, and it's very difficult at this stage to cover all in the detail. So I will just give an idea, right? And after that, I will try to cover them in the next video series one by one. Because if you look at here and focus on the material sections, we have so many details that are necessary to cover, and we can look at here that there are too much to discuss, and it's more than enough at this stage to consider them. So I think I will only discuss them, and then when I'm doing practical projects on this series, I will try to cover them one by one. So these are more than 50 to 60 video series there that are required for defining all these sections. But this is the backbone of the STKO. These two these two definitions series, this one and this physical property and this element property. These are the backbone. Then the condition is not so much difficult as well as mesh and analysis. If you learn this definition, this physical property and this element property, then I think you almost learn 70% of STKO. And these element types require knowledge of OpenSees. So I'll try to just explain them in the property module one by one, and try to cover this in the single video before going further. Allahu Akbar. So let's try to practice the local access in this discussion. First, we need to understand why local access are important in finite element analysis, right? So the local axes are important for some of the reasons which I will try to explain here. The first reason for the definition of the local axis is the orientation of the element properties. For the beam elements and special type of elements, the local coordinate system defines the orientation of the element geometric and material properties. and this is important for accuracy of the representation of behavior of the element, especially for anisotropic material or elements with directional properties like beams and shells. And another thing is sometimes we need accurate representation of loads and boundary conditions. So the local axis determine the direction of the applied load. It also helps in the determination of constraints and other boundary conditions on the element. For example, if we talk about the truss elements, so aligning these correctly with the element orientation is very necessary for the analysis to accurately capture the real world behavior. Also, for the interpretation of results, the local coordinate system is used to express the computed results like stresses, strains, and internal forces in an appropriate direction for that element. So, misaligned local axis can lead to inaccurate interpretation of the analysis results. Also, if you need consistency across the model, it is important that all the elements in your FEA model have their own local axis consistently oriented. And if those are inconsistent local axes present in your model, that can lead to the discontinuities or errors in the overall solution sometimes. So, to summarize this discussion, properly defining and aligning the local axis and local coordinate system for finite element models is critical for ensuring that the FEA model is accurately represented and the physical system being analyzed is accurate. The loads and boundary conditions that we are using, the properties utilized are accurate in the analysis result are just trusted properly. Um, if we talk about the effect of the local axis and the accuracy of the results, so it's very important because local axis play an important role in the accuracy of FEA results for several reasons. Some of them are your element orientation. So local axis define the orientation of the elements. It ensure that the geometry and material properly are assigned correctly with the physical structures being analyzed, and this alignment is essential for accuracy because it represents the behavior of the element in your APM model. And if you talk about the load and boundary conditions, so properly aligned local axes ensure that applied loads, constraints, and boundary conditions are correctly oriented with respect to the elements. And if we have misaligned local axes, that can lead to inaccuracy in the analysis results. Also, for the interpretation of results, the local axis, as I defined previously, is important. And for consistency and continuity, orientation of the local axis across the elements in the model is critical for ensuring continuity and avoiding discontinuities in the analysis. So that's very important. And sometimes we face some challenges in aligning the local axis definition. That is, automatic assignment. Some software provide automatic assignments, so that's very uh, challenging to prone to the potential misalignment in accuracy and the simulation. And manual adjusting is also challenging. Also, orientation requirements for the local axis for understanding is difficult to achieve, and the consistency is also challenging. So that is covered by the drafting techniques. So let's just jump into this discussion. For example, if we have an element, let's say we have this as a line element, and if I define a geometry, um, okay, let's define a rectangle. So for x-axis it is minus 25, for y-axis it will be minus 25, 0, and it is 25, 25, and 0. And let's just delete this one and zoom it to the extent here. Also, Let's define a line. Let's go to geometry. Sorry, first let's define a line and call it with coordinates x50, sorry, 100, 0, 0, and 100, 0, 100. So let's say like this, and then 200, 0, 0 for the another point. And let's go to geometry and go to sphere. We can define it any direction. So let's say I define 50 as a radius. Then I can move it if I want to move it. So I can then explore this to convert it to the surface. I previously defined all these things in a very detailed way. Anyways, let's go to geometry and surface and planar, this rectangle, and press enter. So I define the surface here as well. So we have rectangle, we have this line, we have this point, and we have sphere, and we have plane surface here. Um, let's go to the property module and go to the introduction module here. Sorry, the a local axis module here. And let's define a rectangular local axis here. So for local axis, uh, first let's try to define the local axis. So for example, if I want the global axis to be a line with respect to a local axis, I can define 0, 0, 0 as an origin and x to be 1 as an origin, as a first point. So let's say I have this local axis for now. What look at the second point, x-axis, so 1, 0, 0, and the third point are xy plan. So for xy plan, this will be 0, y will be 0. Let's make z1, so it will be in this direction. If I make z minus 1, it will be in this direction. You can see here, right? Right? And you can look at here, right? X-axis is defined here, so you can control it here. So for example, I make it 1, so it is in this direction now. So I define this local axis, and if I want to delete this local axis, I can define it from this region. Similarly, I can define another local axis, that is cylindrical local axis, and call it CYL, and the first point will be NG 0, 0, 0. The second point will be an x-axis, so 0, 1, 0, 0, and the third point is an xy plan. So for xy plan, the third point will be 1, 1, and 0. So I define the cylindrical coordinate system as well, and similar to this, I can define the spherical coordinate system as well. So SPH, the first point will be origin. I'm just doing it like this way because I will assign it to any values that are assigned here. The second point will be 100, and the third point will be 110 to make it similar to the same orientation. We can rotate it, we can decide the axis properly, and we can STKO offer a good way of orienting them based on the direction it offers here. So we have three kind of local axis definition here. If we go to delete options, we can select them and we can delete whatever we want to delete in this local axis definition. If we want to edit this, for example, if I click on it and if I click on OK, so we can convert it to a coordinate system in this way. And if not, then we can cancel that command here. So we can edit them as well. We can assign them. For example, if I want to assign this rectangular uh, local access to any region, then this is assigned here. So it will show us the status here as well. And if I want to unassign them, then I select the local axis and I select the geometry and click on here. So that's how we do it. And from this region, we can show the option of the local axis that are assigned to this regions here. So by default, the local axis will be with respect to the global axis, right? And if we assign a definition to any kind of local axis, then we can show them by this way as well. So let's say I want to delete the cylindrical local axis from this one and press enter. Then, sorry, not here. I want to unassign the rectangular local axis from this. Then we can see here that those are unassigned. So let's say I want to remove this one, right? Only one local axis is remaining, that is rectangular local axis. And if I want to delete this one as well, I can delete it from this region properly. So now if at this stage you can see here that the red axis is in direction with the local axis of the global coordinate system, and we can see them here, the coordinate system that we are observing here. So if we try to remove that, we can remove it as well. It will not create any trouble for us, and it will be easily removed. Um, let's say I want to create a new local axis rectangular in the opposite direction, um, and then I define the origin. So this will be the origin, and for the second point to be on x-axis, let's say I want -1, 0, 0, and in the xy plan I want -1, -1, and 0, and press enter. So this is completely opposite to the local axis. And if I assign this rectangular axis to the other axis, then I can observe here that the orientation is changed with respect to the local global axis that we have, the local axis that we have previously defined. So to the nodes, that local axis is assigned here. So you can create new one local axis, you can delete it, you can edit, you can assign, and you can unassign here, right? And this local axis will be available in the modeling tree in the details here, right? So we have rectangle, we have line, right? And we have shape, the vertices, and all these details that I explained previously, and all these definitions here. So work plane selection set here, work plane selection set, local axis, geometries, and interactions are completed, and then we are switching to the definitions here. So it's your choice if you start from this region or if you start in the modeling tree. It's completely up to you, or if you want to look at here and you want to do all these definitions here. So it's not a difficult thing to understand. First stage, you need to understand the process, that how it works. Then in the later stage, when you get familiar with the interface of STKO, you will be able to work on it, and you will be able to follow any training series that are offered by the ASD software company and technology. So then you can follow the trainings very easily based on these conventions here. So this is about the local access definitions. This is about the local access definition, and then we have the definition. So this definition is related to the uh, models that we are using in our uh, data, such as RAM and other considerations in the modeling environment. So local access is covered, the definition is remaining. You can further work on it by the display grids as well. And based on the property module, if we switch to the definition, uh, definition is related to the physical properties, and to define and assign the physical properties to the model, we can then go to the properties module and new property, and where you can define the materials. And also you can work with the material, other attributes, filters, etc. You can do whatever you want with your model. So these are related to the physical properties, right? And you can work with the shaders, you can change it whatever you want, whatever section which you do, you can do it here. So for physical properties, all those material etc. are defined. For element properties, all those special types of elements in the joints etc. You can use them. And if you have a definition like the time series etc., you can use it in your analysis. For example, if I have a load history, then I can define a definition here that is, for example, a time series, a linear, a path, triangular, whatever I want to do. And after taking some time, it will show us with the factor, and we can assign the factor for it. So this is kind of a load that it is defined here, right? For example, if I convert it to 2, it will increase the amplitude to further detail way. And if you click on the button here, you will be directed to the information associated with this term that are present in the OpenSees documentation here. So this represent in OpenSees a tag in a linear factor. So the linear factor is basically this factor, that how much you are going to scale your amplitude to, and this is the time series tag object here. So on this discussion, you can find out a lot of useful information here. So with definition and with cloning, then you can clone them. For example, if I define a time series here and call it time series linear, right? L. And I went to the time series and I went to 1 here, and I click on OK. So remember the code tags here, the color is gray, so it is not assigned here. If I want to clone it, so what does the clone mean? The clone basically mean copying this one. So you can see here we have this copying definitions here. If we go to the edit series, we can edit those. For example, if I select this one and I switch to a Coulomb definition here, and I define this to coefficient of friction, mu coefficient of friction. If I switch to limit curves, rotation, so I can define all these informations in a detailed way, and then I can go to the relevant information available on the OpenSeas documentation as well here. So this is a good way to understand all these information, and you can then do it as per your requirement. So there are some kind of detailed information available when you are working with it on the model. So we have some random variable beta etc. That are related to the input properties when you are working with it for the loads etc. and other material definition. So all these are distributions. Sorry, this is for the test distribution which you can work with, and I will in detail explain them one by one. For example, if I click on the ground motion, I can select the station here. I can select the equation of motion. I can select the other details. and all these information. And for more of the understanding of these terms, I can go to the real motion and the OpenSees documentation to understand what is going on in this model. So if you use these informations, then you can use them in your OpenSeas and STKO software. So the definition, for example, if you go to triangular, if you go to pulse, these are various kinds of definitions that are required for your analysis. So it's like amplitude in all those terms, but it's not only associated with amplitude because the definition contains various kinds of information that are required to it. So it's not only about the amplitude. Only if it was only about the amplitude, so then sinusoidal decay function and other functions will be present in this. And so this is about the definition. I'm not going to do a detailed discussion on it. I have planned to define a another video series in which I will explain these definitions one by one, and I will try to cover these in a separate video to have a better understanding on these. You have to then watch this video series, and I will try to include a detailed way of including this information. After that, this physical properties is related to the materials and section stuff in all those directions. And for example, if I want to use the uniaxial material, and I want to use basket behavior, and if I want to use benching for element, and if I want to use limit state elements, and for example, if I want to use beam column element section properties. So these are a lot of informations available in this section, so you can then use them. But I have planned to, as I mentioned, this is the backbone of the STKO, this definition, and this element properties, and this sorry, physical property and element property. So I have planned to record them in a detailed video series. Here we have the options for the special element properties editors, and we can use them. For example, link element, two noded link element. So if we look on it, and I mentioned this in the previous videos. Before that, I used the interaction as well. So for example, if we are using two noded link element and we are trying to simulate the spring element, so either we can use zero length element and non-zero length element. There is a detailed discussion on the OpenSeas documentation website about these two noded link elements. So if we go to two noded link element, we can access the OpenSeas documentation, and here a detailed discussion is given on two-noded link element, and this two-noded link element is used in many research articles in their instructions definitions. So understanding them is very important, and you have to be very careful about the selection of these spring constant and dashboard constant for the definitions, and local axis association as well, because local axis, here the assignment of local axis is very important. For example, if you look at this region, the I node and J node, if you misinterpreted the local axis, then you will not have any kind of sensible results in your analysis. So this is related to all those terms, and we can use RC giant model 3D element and all those information associated with our model. And after that, this is the color coding based on element properties and physical properties. Since we have not assigned any element in physical properties here, so which means that this visualization is currently not working for us. So this is all related